Dr. Jess Wade from Imperial College London. So she's a Royal Society University Research Fellow and a lecturer in functional materials at the Department of Materials at Imperial College. Her research really considers new materials for optoelectric devices and quantum technologies. And outside the lab, she's also involved in several science communication and outreach initiatives. So Jess Wade is a professional science communicator. She has a lot of experience in this, and she's committed to providing improving diversity in science, which we've been discussing here, both online and offline. She's written 2 children's picture books, Nano, the Spectacular Science of the Very, Very Small, and Light, the Extraordinary Energy that Illuminates Our World. And so Jess is going to talk about materials for quantum. And so without further ado, I think we can play the video and welcome Jess.
Hello to everyone, my name is Jess and I'm a research fellow at Imperial College London, and today I'm really excited to talk to you about materials for quantum technologies and particularly why I find this such a fascinating area to work in. And I'll tell you a little bit about the types of materials that we work on in my research group, which are these beautiful molecular systems that have huge potential in quantum technologies, particularly when we think about the symmetry and the shape of those molecules, and then a little bit more about some of the technologies that we're developing at Imperial. I don't know if any of you have heard about Imperial College. It's a university in central London. I like this little cartoon map of central London. Way down here on the bottom right-hand corner, you can see things like the Houses of Parliament and Big Ben that you might be familiar with, or Westminster Abbey, and then Buckingham Palace, where the royal family live. And then over here we have this big park, and this big park is actually called Hyde Park. And next to that, you have a few cultural centres, which are really important. One is the Royal Albert Hall, which has huge performances of beautiful, beautiful music. One is the Natural History Museum, which is where they have all of a collection of natural history from kind of dinosaurs onward. You've also got the Victoria and Albert Museum, which is a big centre of culture and the arts, the Science Museum, and then this whole region in red is actually Imperial. So this is the university I work in, and this is actually the halls of residence, so where the students live if they go to Imperial. And we're kind of in this hub of science, arts and culture, and are really, really connected to the surroundings that we're in. It's actually a world-leading research university for science, technology, engineering, medicine, and business. And currently it's second best in the world for all universities. But what we're really passionate about at Imperial is to try and understand more of the universe and improve the lives of people within it. I thought it would be cool to tell you about a new partnership that launched from Imperial last year. It's called Global Ghana. And this is a regional hub for collaborations that supports research, education and innovation between Imperial and people and researchers in Ghana. It grows on a big network of African universities partnering with Imperial, and particularly around kind of how we can share ideas, share new innovations, share new breakthroughs, train students better, and actually help both of our governments understand how important science and engineering are. So there's a few different activities within this network, particularly that I thought might be interesting to everyone in this audience, but around kind of maths, particularly student placement, innovation and things like that. And actually really cool, when I was looking up some pictures to try and show you about this fantastic partnership, just a couple of weeks ago, our mayor here is in the middle in this navy blue suit. He's called Sadiq Khan. But he came over to Ghana as part of this massive celebration. So not only does London love Ghana, but Imperial loves Ghana a lot. So if there's anyone after this talk who wants to talk more about that partnership, I'd be very happy to. So our quantum centre at Imperial, which is called Quest, is focused on translating fundamental understanding and discovery in quantum science into technologies that benefit society and the economy. Across all of our university, it has about 150 different academics involved with it, and a lot of research students who are really passionate about this kind of translation of what we understand in physics labs into technologies that help everyone in the world and the universe, maybe. We focus on a few different things. We focus on fantastic research in 3 priority areas, and that's materials for quantum internet, so quantum networking, and also applications of quantum computing. And within that, we have 6 themes, which is navigation, communications, computation, sensing, quantum for fundamental physics, and also foundations of information science. We're really passionate about public engagement, so if anyone in this audience is keen to help the public and young people understand quantum, I'd be really happy to talk about that. We've been thinking a lot about skills gaps, so how do we get more engineering graduates passionate about quantum technologies? Because if you want to build a quantum computer, you need more than just a physicist with an idea. You need an engineer who can translate that idea into a reality. We've thought a lot about engaging policymakers, about how we work with other countries, particularly actually if there's anyone who wants to come over and see our quantum centre, and be really happy to host you, about innovation and also how we have better access to infrastructure and equipment. So this is kind of Quantum at Imperial, and I'm part of that, which is incredibly exciting. I know you've had a couple of days now of quantum and this celebration of the International Year of Quantum Science and Technology. I'll try over one slide to tell you about why I think this is such a phenomenal year. So we're 100 years since Schrödinger developed the maths for this wave function. And this is a description of quantum objects that describes how a quantum state of a system changes over time. So that's why we're celebrating the International Year of Quantum Science and Technology this year. But I find it's kind of amazing how much had to happen before we got to this point that Schrödinger could write down this equation for us to ever even conceive that we can translate this fundamental quantum physics into a technology in the first place. We had a huge advancement in our understanding of light. So there was a guy called Christian Huygens, who you may have heard of, and he first proposed this wave-like nature of light in the 1600s. And he explained that light was a longitudinal wave, and that was passing through this substance that scientists at the time called an ether. And this could explain most of the properties of light, including diffraction. And everyone here is probably an expert and knows that diffraction is this kind of spreading out of waves as they go through a barrier. Newton came on about decades later, and everyone loved Newton. If you've heard of Newtonian mechanics or Isaac Newton, a big celebrated scientist. And he said actually light didn't travel in waves, it traveled in these little particles called corpuscles. And that could explain some of the properties of light. It could explain reflection and refraction, but it couldn't explain diffraction very well at all. And it would be 100 years later, actually, for Thomas Young, who was a really big fan of Newton and who'd read all of Newton's books about light. But he used an experiment called the double slit experiment, which is now very famous, to show that when light passed through two slits, actually the pattern that you saw on the screen, this interference pattern, would show these bright and dark fringes that could only happen if light was a wave. So we had the wave-like nature of light. And all of this discovery came about at the same time that we were starting to understand the structure of atoms. We had this kind of plum pudding model put forward by J.J. Thomson. So this is looking inside an atom now, and this spreading out of positive and negative charges from your protons and your electrons. And everyone who's done any physics knows that this isn't the actual true structure of an atom. So J.J. Thomson proposed this in 1904. We had Rutherford coming in just 5 years later, who said actually the positive charges, the protons, were concentrated at this dense core called a nucleus, and then some kind of electrons are whizzing around that, and he didn't go into much more detail than that. But no one could explain how the electrons were orbiting this positive nucleus in such a way that they didn't just crash into it. It turned out that the key to this explanation was this quantization of energy. The energy of things like light and also electrons are quantized, so it can only take on specific discrete values. Actually, this quantization, which here is shown by this kind of step-like diagram, it fixed a lot of problems. It explained that a photon's energy, which is in this equation E, is related to its frequency or its wavelength by this thing called the Planck constant. So hopefully you've all heard of that. But this was really useful for scientists. So we managed to say actually this quantization was happening. Electrons, photons, these packets of light, couldn't take on any value. They had these discrete values, and that actually was really key to being able to explain what the center of a nucleus was. A few years later, after Planck said that energy was quantized, Einstein explained that actually electrons and photons, which we now think of as these kind of fundamental quantum objects, could exist as both waves and particles. So the diffraction pattern that you expect to see after waves pass through this double slit, well, it's exactly the same if electrons pass through a double slit as well. This is a little animation showing the diffraction pattern that emerges when you have electrons going through a differently spaced slit. So it has to accommodate for the fact that electrons have a slightly different wavelength to visible light. But you start to see this interference pattern. So we've come a long way, right? We understand light now. We're getting closer to a description of what the structure of an atom looks like. We've understood and we've taken in this advancement from Planck that the energy of electrons and photons was quantized, and Einstein coming along and saying, actually, they have this wave-particle duality, which is kind of funny given this discussion between Newton and Huygens and Young about the wave-like nature of light. Quantization actually let Bohr, a few years later, describe the structure of an atom even better. Electrons were moving specifically in these circular orbits, and as they transitioned between those orbits, as they made transitions between these orbits, they actually emit and absorb light of particular colours. So all this build-up let Schrödinger get to this point that he described this wave equation, which described how the quantum properties of these electrons and photons changed as a function of time. He also explained that quantum objects can exist in two energy levels, so they can exist in something like a 0 and 1. And if they can exist in those two energy levels, then they could be in a superposition between them. This is kind of nicely demonstrated by flipping a coin. You have your kind of state of 0 and your state of 1, which could be your heads or tails. But when you flip that coin and the coin is in the air, it's in a superposition of both of those states. And it's actually superposition that lets quantum computers perform calculations on multiple possibilities at the same time, which speeds up computations and lets you do completely different type of computing to what you could do on a classical system. So Schrödinger took in all of this science from these extraordinary people who came before and said, actually, not only can we describe these properties using this wave equation, but superposition falls out of that. And actually, entanglement, this idea that you can prepare quantum systems to share a quantum state, even when they're separated by very long distances. And this lets quantum systems perform calculations on lots of variables simultaneously, and which makes them really ideal for optimization problems or when you want to explore a huge complex parameter space incredibly efficiently. So this is kind of my quantum 101. And the first kind of quantum revolution, so this understanding of electrons in solids and packets of light, these photons, gave us things like digital electronics. It gave us a lot of medical imaging. If you've ever had an MRI scan, that relies on those spins, those unpaired electrons in hydrogen. And it also gave us lasers, understanding where electrons were sitting within these energy levels inside an atom, let us create that population inversion that lets you create these technologies called lasers, which underpin so many photonics, optoelectronics. Our whole understanding actually about materials comes from being able to manipulate lasers. The next quantum revolution, and why we're so excited and why you're celebrating today in Ghana, and there's been celebrations all around the world actually for the past year, uses these exotic quantum phenomena, things like superposition and entanglement, to make new types of computers, clocks, sensors, and imaging systems to have new capabilities that we've never been able to do with our technologies before. So this is why we're so excited about it. But there's a lot of science and engineering challenges that we have to overcome to make that possible. There are challenges in choosing the types of materials that we'll use for those quantum building blocks, and I'll get to this in a moment. This is what I'm really excited about. So what kind of materials are we going to use to build those quantum technologies, and particularly how good are they? What kind of quality are those materials? How can we get those quantum technologies to have the appropriate lifetime and resilience? You've probably heard a lot or seen a lot around kind of particularly some of the materials for quantum computing are very, very sensitive to their environments. So how are you ever going to build a quantum computer at scale and where you can connect these different qubits together and be able to perform quantum computations for a long time? What kind of environments do we have to keep these quantum systems in? You may have seen some of them, particularly for superconductors, have to be kept extraordinarily cold to maintain these quantum states. That's not very good for the environment around them. because actually it's hugely energy intensive and power intensive to keep things so cold, so to keep things close to absolute zero. How do we initiate and read out these quantum states? Do we do it using light? Do we do it using electricity? Do we do it using microwaves? How practical is it to manufacture these quantum systems? How can we integrate them and connect them together? And actually, how do we standardize and benchmark these different quantum components? If you're making something like a quantum photonic computer, you have to know that when you buy your laser from your collaborator, who could be in the UK, they could be in Ghana, they could be in the States, how do you know that every single laser you buy performs exactly the same as every other laser? How do you know that every time you make your superconducting qubit, it performs exactly the same as all of the others? So these are the kind of engineering challenges that we have to think about to try and make those quantum technologies possible. So at the core of these quantum systems are these things called qubits, and these can exist in these superpositions that give us this huge opportunity in kind of parallel processing and massive speed advantages over classical computers, and also that immense sensitivity to their environment that makes them really, really good sensors. And to make these qubits, you have to have a few different requirements of your materials platform. One is that you've got some stable energy levels that don't shift around too much, so that's kind of one key one. Another is that you can control these energy levels. You can put these qubits into superposition somehow. So you've got a materials platform that doesn't shift around in unreasonable amounts. You can control that, you can initiate it. You've got some way for these qubits to interact with each other, so you can perform your calculations. And then you've got to have some way to measure your qubits so you can extract that information, that kind of result from that quantum computation. And it actually turns out there's a huge number of different materials platforms that you can use to do that on. And this is something that's kind of really excited us as scientists to think about it. Actually, at Imperial is actually the leader of a UK network called the Materials for Quantum Network, who are thinking about all of these different materials platforms and some of the challenges we have associated with delivering these quantum technologies made out of them. And so that includes 2D materials, it includes beautiful molecules that I work with, includes semiconductors and photonic systems, solid-state defects, so that could be nitrogen vacancies in diamond, spin and topological systems, and superconductors. So we're really thinking about these materials at the heart of the quantum device, as well as the systems-level materials. So these are materials in the supporting infrastructure. So you've got kind of the materials that are there, controlling these quantum states, performing these quantum calculations, reading out information about their environment, and then also the materials that you have to use to make those precise control electronics, or some of the optics that you might need to initiate these quantum states, or some of the systems that you might need to build around your kind of vacuum chamber or your vibration isolation. So there's an awful lot of material science that we have to optimize before we can get to a state and that we can build these quantum technologies. Some of the ones that are particularly attractive and particularly exciting at the moment are these kind of trapped ion qubits. And then they start with a single charged atom, so a single charged atom that's been trapped by an electric field. To be used as a qubit, you've got to keep these really, really close to absolute zero. And the qubit lives inside the internal energy structure of that trapped ion. You use focused laser beams to prepare that qubit, and then you manipulate it using different types of light. And so some of these trapped ion qubits are some of the most exciting materials platforms at the moment. Qubits made from superconductors, they rely on the quantum behavior of electrical circuits, which have energy levels that are similar to atoms. In the simplest case of these superconducting qubits, you can store information in the amount of charge that's sitting on a small island of superconductor within this superconducting circuit. The low energy state has some baseline charge sitting on the island, and the high energy state has a single extra charge. And the island connects through another block to another block of superconducting material. And you kind of manipulate this using pulses of microwaves. So you have trapped ions that use the internal energy structure of these trapped ions, and they're trapped by using laser beams kept close to absolute zero. You've got qubits, made out of superconductors that use this quantum behavior of conventional circuits. And then you have photonic systems. And now these are kind of interesting, these photonic platforms for quantum computing. And they can encode information in the polarization or in the phase or something like that. They're kind of sometimes called flying qubits. So they use these quantum properties of light and encode their information like that, and then build these quantum computers out of them. There's a lot of literature on this, so some of the challenges associated with scaling this quantum hardware, and I find it completely fascinating. So if anyone wants to read more, I really like this summary. It was in Science a few years ago. So it's materials, challenges, and opportunities for quantum hardware, and I'd be really happy to talk to anyone about it if you want to talk about these different materials platforms, because that's actually really exciting, right? In kind of superconducting, or in photonics, or in trapped ions, or in molecules, who's going to win? Who will win will be the quantum technologies that offer the most reproducible, robust control of quantum states in a way that's environmentally friendly for us enough to be able to scale that technology. So this is a really, really fantastic paper. And then I found this table when I was putting together this talk that goes through the different quantum platforms. So superconducting, photonic, cold atoms, trapped ions, silicon, kind of quantum dots, NV centers, and topological systems, which companies are currently working with these different platforms, and then some of those quantum properties, so things like their gate fidelities or their coherence times, and then the kind of pros and cons of these different approaches. So I really, really like this table if you want to take a look at it later on. I thought I'd just tell you a little bit about molecules, because I'm really excited about molecular systems for quantum technologies. They're really, really interesting. They have really, really high brightnesses and stable emission and absorption, which makes them useful for quantum photonic technologies. They have accessible quantum states, which we can access at room temperature. We can actually process them in really simple ways, so we can even print them sometimes onto flexible surfaces. What's neat about molecular systems is that you can tune their chemical properties, or you can tune their electronic and optical properties by changing their chemistry. So you have this kind of rich toolkit of organic chemistry, which gives you kind of near infinite tunability. So if you want something where you can initiate a quantum state at a particular wavelength of light, you can do that by thinking about the chemistry. And then also, because they're created using this organic synthesis, every single time you synthesize a molecule, it behaves exactly the same as all of the other synthetic counterparts. And so you have huge, huge precision in the reproducibility of these molecules. They have really well-defined transition dipole moments, so you can use them as really precise sensors for magnetic and electric fields. And then they have very, very weak spin-orbit coupling. So their electronic structure comprises of all of these different electronic excited states, which you can access optically. So I think molecular systems are hugely exciting. And the research that we do in my group is thinking particularly about the chirality of these systems, so the handedness, the symmetry of these materials, and how we can use that to control things like the twist of light or the spin of electrons. Chirality is this massively interesting property that manifests across multiple different length scales in the human-made and the naturally occurring world. So from the subatomic, from things like electrons and photons, we see this handedness there. So these can exist as left or right-handed non-superimposable mirror image counterparts. So here we've got spin up and spin down electrons, or left and right-handed light. We see chirality in molecules. These are some beautiful molecules called helicenes that I work with a lot. We see chirality in biomolecules, so at even bigger length scales now, in things like DNA and proteins. And we see chirality in things like shells and fusili pasta, and some beautiful beetles have chiral nanostructures in their shells. And actually in plants, and the light that comes to us from distant galaxies. So chirality is a fascinating design rule that has given nature unparalleled opportunity to perform complex processes in an efficient way. And what we're kind of interested in is, particularly when you've got these chiral molecules, how does this twisted wave function of the electron, so if you imagine you've got your molecular structure, and actually the electron orbitals within that have this helical structure. And actually it turns out when we've got a chiral electron orbital, we can use that to control the polarization, emission of light, and also the polarization of charges. So some of the technologies we've been working on is thinking about using that circular polarization emitted by twisted molecules to make even more efficient displays, to try and create molecules that we can use as single photon sources of twisted photons to encode information into quantum photonic computers. And actually, if we take single-handed molecular systems, how they can act as spin filters for electrons, even at room temperature and without magnetic fields. So this is hugely exciting material science we're now doing, thinking about the chirality of these systems. Just to give you a sense of the UK's quantum programme, before I kind of wrap up and tell you a little bit about some of my favourite technologies, the programme started in 2014. It was a big investment by the government to really think about how we bring scientists together with engineers to solve some of society's most complex problems using quantum. And we had a national quantum strategy that came out in 2023. And from that, the government gave us these really cool quantum missions. And the first mission is that by 2035, we're going to have UK-based quantum computers that can do 1 trillion quantum operations. And by 2035, we'll have a quantum internet that will be deployed at scale. And then the final 3 missions are all around quantum sensing, and which I find really neat. So one of them is that by 2030, every NHS trust will benefit from quantum sensing-enabled solutions. By 2030, we'll have quantum navigation systems on aircrafts, and by 2030, we'll have quantum sensing systems that will help people building new infrastructure or in transport or in telecoms. So the government has set us as scientists really ambitious tasks to try and deploy some of these quantum technologies, to stop talking about making them and to actually making them and deploy them. And so I was going to tell you about a few of them. I was going to tell you about NV diamond magnetometry, but I'll just show you a few of these examples. And this is a really neat example from a research group in Nottingham who are trying to create an alternative to brain imaging. And this is what you might have had if you've ever been to the doctor to have an image of your brain. This is something called magnetoencephalography. And what you see from this picture is just relative to the scale where you'd be sitting down on this nice chair. The sensing system, the medical imaging system is gigantic, and it's gigantic because to detect the magnetic fields associated with your brain, you have to have a really high precise sensor that has to be kept extraordinarily cold because it's built using such old-fashioned technology. The team at Nottingham created this really cool quantum magnetoencephalography system, which actually works by having these tiny, tiny sensors at the end of these optical fibers. And they actually have a glass cell that's full of these rubidium vapor, and they have a laser and they have a photodetector. And they shine a laser on this rubidium vapor and they measure the light that gets to that photodetector. Rubidium has an unpaired electron, it has a spin, so therefore it has a magnetic moment. So if you shine circularly polarized light, so chiral light, onto this rubidium vapor, you make all of those rubidium atoms align and you actually maximize the laser intensity that gets to your photodetector. So when there's circularly polarized light shining on your rubidium, you get really, really high intensity light hitting your photodetector. If there's a magnetic field nearby, particularly associated with the brain function, how your brain's operating, you actually rotate some of these rubidium atoms because they've got these unpaired spins, so they have a little magnetic moment. And actually that rotation has an impact on the light intensity that gets to the photodetector. So this combination of this light coming from the laser and the magnetic field of your brain results in the intensity dropping at that photodetector. So you've aligned your molecules using this twisted light, and then when you apply a magnetic field, you change the intensity that gets to your photodetector. So you can use that to read out how your brain is functioning, which is just the coolest thing ever. My friend Joe, and I won't have enough time to tell you about this, but my friend Joe actually uses exactly the same rubidium vapor to be able to perform some kind of really cool navigation. So they do this quantum navigation by measuring how much rubidium atoms trapped inside this laser-cooled system move as you're accelerating and decelerating during transport. So what Joe can show with this type of approach to this quantum navigation, that if you know very precisely where you start from, you can build this quantum accelerometer by tracking, actually using atom interferometry, tracking the acceleration and deceleration of these rubidium atoms within this laser-cooled system, and use that to precisely work out where you are without having to have access to GPS or other technology like that. And he's demonstrated it on a London tube and also on board a Navy ship. So you can do all of this without accessing satellites. You have an inertial navigation system, which is very, very important for when you're in scenarios where you can't access a satellite, like when you're underground or under the ocean, or you don't want to access a satellite because you don't want people to know why you're traveling to the pace that you're traveling to. I told you before that we're very passionate at Imperial about communicating and thinking about quantum technologies, and we've had a lot of fun over the past few years celebrating Quantum Day on April the 14th, because Planck's constant in electron volt femtoseconds is 4.14, which is how Americans write April the 14th. But also at our science festival, where we take kind of beautiful visual interpretations of quantum, or sometimes we do it with dance. In the bottom left here, we have quantum tunneling, and we've got celebrated and generated a quantum disco. Or sometimes we introduce the public to quantum through poetry and through meditation. So we're really, really committed to inspiring a new generation of quantum researchers and helping the public understand these technologies that will transform their lives. Finally, if you want to read any more about quantum, my friend Dominic, who's got a YouTube channel called Domain of Science, has these beautiful posters and YouTube videos where he goes into different types of qubits that companies are making, and also the different ways quantum technologies can be used, their advantages over classical approaches, and different physical realizations. So I could not recommend this highly enough if you want to learn a little bit more. Hopefully, I'll be able to take some questions now, but if you've got any more questions, or if you're particularly in London or you want to know more about Imperial and Imperial Global Ghana, then please drop me an email at jessica.wade@imperial.ac.uk. Thank you so much for this amazing opportunity. Happy International Year of Quantum, and sending so much love and scientific enthusiasm to Ghana. Thank you.
Oh, thank you very much, Jess. As usual, I already knew that was going to be wonderful. But thanks really a lot. Okay, so questions? Students? Anybody? So while they're thinking about that, it was a great idea about the coin flip. I mean, whenever I talk about probability, I mean, that's the canonical method, right? The coin flip. And we're always talking about probabilities anyway with superposition. So that's actually a good idea. So anybody got a question yet? By the way, we have people online. Do I have any online questions? Okay, not so far. That's a shy crowd. So Jess, what was the Imperial delegation that coming here to Ghana? Because everybody obviously here is in Ghana. Was this a university? Was it an entrepreneurial program? Was that what I understood?
Yeah, it's a program actually. What we're starting to do in the UK from the quantum ecosystem in universities is spin out these ideas to make companies. So there are lots of physicists working with engineers to say, we can do this, let's build it, and let's build it into something that's useful for society. And that's something actually that we're trying to replicate with our friends and colleagues in Ghana, is that kind of tech transfer. So that's what I think the delegation came out recently to support student innovation. So to have competitions for innovation and entrepreneurship for students, kind of startup seed funding competitions, but also to help universities with that tech transfer process of turning scientific demonstrations from kind of being a benchtop thing in a lab to something that actually helps people in society.
Okay, right. So, and as far as skills go, because there are also some engineering students here, they're really shy, but they, for them to go into the quantum science and technology sector. So, what kind of skills? Anything specialized, or just good old-fashioned analytical thinking and problem solving and soldering skills?
Well, this is such a good question, actually, and it's one that we're thinking about a lot when you try and build a quantum company. You can kind of imagine it like a triangle, and at the top of the triangle, you need all of your physicists who come up with these really cool phenomena and how to create them in some kind of hardware platform or algorithm. But then actually underneath that, you need a lot more engineers who are just really, really good at electronics, at connecting different components, at making really complex pieces of kit to talk to each other in a proper way at the right time domain, to be able to initiate, control, and read out these quantum states. So you need actually in a quantum company an awful lot more engineers than you do the physicists who come up with these ideas. So what we're trying to do in the UK and also the US is really think about, and we'd love to do this with our friends in Ghana too, especially through these partnerships, through the ICTP or through SPIE, who I'm here with I'm in San Diego with at the moment, and have a big focus on photonics education in Ghana, is actually upskill all of those fantastic engineers who aren't quite thinking yet, I could become a quantum engineer, but have huge capacity to contribute to these technologies.
Yeah. Okay, actually, we do have some people here from Henry Martin. Is Henry here? I don't know. Oh, yeah, he's back there. Okay. So he's working with Robert Sewell. So you know Robert. Okay, so and Peter de Groot. So they're both working at this GNUST. And so Henry's here. So it's actually, I think there's a lot of great ideas coming along. Any questions yet?
There's a question in the chat I can take. That's a really good question, saying, can you explain how
yeah, go ahead, please.
Navigation? So it's a question saying, how do the navigation systems work? And the two examples I gave are actually using these vapors of rubidium. So in this example, you had a vacuum chamber and you insert this kind of gas of rubidium, and then you use these powerful lasers to cool these rubidium atoms. So they're cooled down to just above absolute zero. And when they're this cold, the wave-like properties of the rubidium become really important. And they're impacted by the acceleration of whatever the vehicle is in. So if you've got your vacuum chamber, and that's on board a subway or a Navy ship or whatever, you cool your rubidium atoms down using these lasers. And then when they're that cool, the wave-like properties of those rubidium is impacted by that acceleration and deceleration. And actually, you can measure that acceleration and deceleration very accurately using atom interferometry. So you use that wave-like nature of the atoms, and you measure that acceleration and deceleration using atom interferometry. And then you very precisely know the speed in which you're moving in a particular direction. So if you know where you start, you know exactly where you are when you make the measurement. It's so cool. Apparently, it's according to Joe, with these systems, it's very easy to do it for movement in one direction, which is why it's really useful for things like when you're on board a tube, when you know that you've got a track. So a train, for example, you know you're moving along a train track, so it can do one directional stuff really well. But actually, rotation is hard to put into the maths. So not only do you need engineers to build these quantum technologies, you also need a lot of mathematicians and computer scientists to help process this extraordinary amount of data that you get.
Yeah, right. So, oh yeah, I got a question here.
Thank you for such an interesting presentation. The automotive industry is going through 1 in 100-year change as well. And I'm wondering, sitting here, how is the quantum technology and materials influencing the automotive industry in your experience, if there's anything like that?
Yeah, this is a really great question. I suppose in a few different ways, quantum computing is something that's very powerful for kind of optimization challenges. So when you're trying to be innovative in new materials for batteries, which they are in the automotive industry, you know, batteries and storage of energy represent a huge, huge challenge to trying to create cars that can last for longer without having to go and charge. Innovation in design of materials for batteries, actually, that's something quantum computers are really good at. Because of that superposition and potential for entanglement, they can scan through lots of possibilities incredibly quickly and then explore that parameter space to optimize those materials. So I'd say in that kind of sense, they're being used, quantum computers are being used by our national grid in the UK for trying to increase kind of robustness to energy distribution. So to collect all of the data from energy distribution sites and how we generate and maintain energy, and then try and do that in a more efficient and secure way. So that's kind of two applications of quantum computing. But then quantum imaging and quantum sensing is something that's being used a lot for imaging in low light conditions. So imaging in scenarios where you might have fog or you might have haze and things like that. So there, quantum imaging comes in as a really precise way to be able to collect very low light intensities and try and understand and see through scenarios that you wouldn't otherwise be able to do. If you're interested in either the quantum computing or the quantum imaging parts, I can definitely connect you to people for further conversations. When I've had conversations with people in transport sectors, particularly around this kind of what are the disruptive potential of quantum technologies, it was quantum computing for materials discovery, quantum computing for energy distribution, potentially this navigation application, being able to navigate without accessing GPS, and then quantum imaging. And in actually the Department for Transport in the UK, so our government Department for Transport, they have someone who is the quantum lead in the Department for Transport. So they have a full-time staff member who is thinking a lot about these systems. And if you'd like to have a chat with him, I'd be really happy to connect you there as well.
All right. Thank you for the opportunity. And thank you very much for the presentation also. In fact, it was very basic and fundamental, and I guess that's another reason why we don't have much questions. And on top of that, it's not really a question, but I think more of I need your inputs on this particular matter. We here as Ghanaians or in the LMIC, we take a lot of chemistry courses around, and from the presentation, I realized that quantum materials or materials for quantum it looks like it's almost always chemistry. You cited examples of seashells and certain patterns in nature, but ultimately it comes down to its molecular level where it now becomes the talk of chemistry. And this is the case where we have senior high schools already taking courses in chemistry. However, it still feels far-fetched from the quantum we are discussing here. Although I think that is the basics for that. Can you briefly take some lights on that for us, helping us to appreciate that the fact that we are doing chemistry here is kind of like the building blocks to materials in quantum we are actually discussing here. Thank you.
Yeah, that's such a fantastic question, and one that I don't think we've got an answer for in the UK, even though you're entirely right. You have to understand a lot about chemistry to be able to build these technologies. I gave the example of the potential of these molecular systems to be the kind of heart of the quantum device, so to be the quantum system that initiates or controls quantum state. So there's definitely a movement across lots of different universities to bring chemistry into quantum in a bigger way. I know in Chicago, they have a huge focus on chemistry for quantum information science. So you can look up that, so kind of chemistry for quantum technologies. But actually, even in this world of NV diamonds, so introducing nitrogen vacancies into the diamond lattice and using that as either a qubit for computing or a sensor of magnetic fields. And this is being used a lot in biology and also health monitoring. That requires that understanding that you got from high school and university and kind of crystallography to understand where those nitrogen vacancies form in that lattice. And actually, there's really interesting, as you said, quite basic chemistry, because if you've got a diamond, and imagine the kind of surface of your diamond, your sensor is as good as how close your nitrogen vacancy is to that surface. So if you've got your nitrogen vacancy here, it's a much better sense than if it's really deep within the diamond. But actually, the closer it is to that surface, the more likely it is to lose its sensing properties. It kind of loses that quantum state. It experiences decoherence. So you've got to create some kind of passivation layer using just basic chemistry that can go on top of your diamond and protect that sensor. So you definitely need the physicists to understand all of those operations of kind of initiating and reading out this quantum state. But you really need chemists, organic chemists actually, who can create these kind of passivation layers to protect that nitrogen vacancy so it keeps acting like a sensor. So I think there's a lot of opportunity when chemists come into the conversation with physicists and engineers to really think about, okay, physics says we can do this, chemistry will tell us how we can do that robustly and at scale.
Okay, please, my name is Martin Luther from Laboni Senior High School. One of the missions the government of the UK gave was that there must be a quantum internet by 2035. Am I right?
Yeah.
Okay, so apart from the whole improving the safety of the user than a regular internet, what other benefits would there be of a quantum internet compared to a normal internet?
That's a great question. So it would be a way to perform these quantum calculations at scale using kind of cloud-based infrastructure. And I suppose you've seen it a little bit from places like IBM and Microsoft moving lots of their quantum computing into the cloud so that people can play around and run quantum algorithms on these computing hardwares. The idea with a quantum internet would be you'd be able to do kind of encrypted communications, so send information in an incredibly secure way. And I suppose that's your point about safety. So obviously at the moment, when we go online, you kind of just trust that people are behaving well and that they're sending information and we know the person who's sending it and we read it out. And there's an element of trust within that. Whereas quantum internet and quantum connections or quantum communication would let you completely encrypt that process because of these properties like entanglement. So it would be more secure communications, and it would let you perform calculations at scale using quantum algorithms without having to have a quantum computer in your high school, university, government, whatever. I think in the future, the idea isn't that every government and every bank and every infrastructure will have their own quantum computer. It's that they'll log into a quantum internet, perform their or log onto a quantum cloud, perform their quantum calculations there, and then transmit information securely through this quantum internet. So there's things around encryption, security, and ease with which you can perform these calculations, which is why so many countries around the world are so keen to build these quantum internets.
Yeah, thank you. That was a very interesting presentation. Well, I'm thinking what are the possibility of really teaming up with one of our local universities to really have a lab, a display lab. I saw that in the 90s in the South African Stellenbosch University. So I remember very well Ghana here when we were going to have what we call a Panafest, where we were inviting these our fellow African black area to come and back that kind of thing. We were trying to have something like that at the University of Cape Coast. That time we had Prof. Salote. They were trying to have it, but it didn't work. But now we have, I know that Imperial College, particularly with the University in Kumasi here, Kumasi, what do you call it, KNUST, where we have really helping really in the area of climate science and technology. In fact, we're involved with the team now with some colleagues at Imperial College, Mark Howell, and all those things. I'm thinking of having a seminar over here so that the youth, the students, will come see these applications. In application, the area of telecommunication, DC, and then lighting displays, and then medicine, particularly surgical. I was telling somebody, if you are doing this, treating cancer, yes, what do you call it, disease, yes, this, then you are using lasers to handle that. It's more accurate, yes, than using just ordinary plain radiation that they are using. Because even though now more expensive, but this is less harmful with less negative effect compared to the main one. In fact, Ghana here, when people get sick like this, where we require this radiation treatment, most of them travel. Those in government and all those things. If you are an ordinary person, then you are here, go to a hospital here. You see, in most cases, the person will think the less not working, this not working, and all those things. So I'm thinking of such collaboration. And there it starts growing. People start seeing it, the applications, and all those kind of things. So think through. Right, fine. Thank you.
It's a great point. I'd be really happy. I'd really love to explore some of the potential for student partnerships, particularly around these technologies that can have real world societal impact relatively quickly. You know, quantum computing feels a long way off because it is a long way off, and it may not directly benefit everyone in this room. But if we got quantum sensing and imaging right, particularly like you said, for medical diagnostics or for something in transport or for infrastructure, then you could directly benefit people at a kind of local scale. And we actually had a delegation come to Imperial a couple of months ago now from South Africa who were really interested in partnerships between Africa and the UK, particularly around that aspect of tech transfer that I spoke about in the beginning. So that kind of idea of getting technologies out of labs and into the real world. The kind of cool thing, I suppose, about some of these quantum imaging approaches, so whether that's for kind of cancer diagnostics or brain imaging, is the hardware is relatively small, You don't need these massive cryogenic systems that you need for superconducting qubits. You can perform most of these types of imaging and sensing at room temperature. And actually, when you see the setups, they're usually just like a little optical table. So you don't need massively complex infrastructure to do it. So we should certainly explore some kind of interesting partnerships or student projects or ways to develop this between the UK and Africa, because there's a lot we can learn together.
Okay.
Sir.
Sorry, what?
Sir.
Oh, I got another student back in the back. You're popular.
I wanted to ask, at what cost can one create one of these quantum devices?
What was the question? At what cost?
Yeah, at what cost?
Oh, that's so hard to say. I mean, at the moment, when you start thinking about the cost of developing these types of quantum technology, you've got to think about the investment in all of the people that made it possible. You know, funding a PhD student who does the research or whatever, because we're still at that early stage of them. I think if you took something like NV Diamond, there's quite a significant infrastructure on being able to make lab-grown diamonds now. So lab-grown diamonds, say they're quite cheap and they're your quantum platform. And then what you need to do is implant your nitrogen vacancies. Actually, that's kind of locked down now. So say that doesn't cost a huge amount. Say that's relatively low cost, you know, putting a number on it, thousands of pounds rather than hundreds of thousands or millions, as if you're building a superconducting platform. Then there'd be the kind of optics and photonics around it, which is again why there's such strength and capacity in Ghana, because of this investment and commitment to optics and photonics. So I think if you were building an individual quantum sensor to detect magnetic fields using these approaches where you can do all of that at room temperature, then probably it would be, I don't know, tens of thousands of pounds to be able to do it, not hundreds or millions of thousands. But when you want, the challenge is when you want to scale these things, right? It's when you want to say, I want to have an array of magnetic sensors and every single one will behave exactly the same. So I need to know that my engineering is right, that the nitrogen vacancies will be in exactly the same place every time. And then that becomes expensive. So just individual sensors and imaging systems, not super expensive. But when they go bigger, that's when you need investment from people who are really, really rich so that we can do this to benefit everyone in the world.
Thank you.
All right. No, okay, one last quick question, because then we got to move on.
Thank you very much, Doc, for that great presentation, especially when you take your time to go through the history of quantum science and technology. It's very exciting about that. There are two questions I have for you. One, do you run BS in quantum science or quantum engineering at Imperial College London? Or at what level do you run programs in quantum?
So we run, I mean, it's interesting. I've had some PhD students who've been doing a skills analysis of where we actually train people in quantum. It comes back to that great question before, saying there's a lot of engineers in the audience here and how can they get into quantum? So there's a little bit of quantum in most undergraduate modules. There's quite a lot, as you can imagine, in physics. There's a little bit in computing, and there's some in different parts of engineering. I'm starting a new module next year, which will run throughout next year for third-year undergraduates from any program to get into quantum. So then we have this option to teach all the engineers and all the business school students and all the medics quantum. So that's quite an exciting new development that we're doing. So we're trying to do this kind of open introduction for everyone to learn together, because that's when you get these kind of truly exciting ideas that are at the interface of these different disciplines. There has been a shift. I know America has some programs that are just a kind of quantum program, so you can choose to do an undergraduate or a graduate program in quantum. I would say it actually comes to the point earlier about engineering skills, that when you train in any of these specialties, you have so much to contribute, you have so much capacity that you can be very flexible in which type of technology you go into. So it might be you do this particular type of electronic engineering and you go into quantum. It could be you go into AI. It could be that you go into communications. It could be that you go into engineering biology. You're basically extraordinarily employable. And that's kind of what I want students to come away with, that quantum is hugely exciting, but if you're great at photonics or great at electronics or great at radio frequency stuff or microwave processing, you will be so employable in all of these different places. And we need people who think, hey, I can take that capacity and that skill I've learned and translate it there, or, you know, they could build that superconducting infrastructure in a much more efficient way. So that's the kind of thing I'm kind of excited about. We don't need a bespoke course. We just need it to be woven into everything we teach.
And secondly, what opportunities do you have for young minds there to further their studies, especially in quantum materials, quantum science, and engineering? Thank you very much.
So we've got lots of opportunities from kind of programs for high school students and schools and primary school students. So we do summer schools for people to be able to come in and try some stuff out. We also do research opportunities for students. So during the summer, undergraduates can do a research placement in a different research group. This is, I think, absolutely fantastic. So you spend your summer, you get paid, and you spend some time working in a research group doing a project. Also, during the final years of students' undergraduate degrees, they come and do a project within a research group. So we kind of have these dissertation projects or these kind of research projects for final year students. And actually, that's an amazing way to think about whether you want to be a researcher, but also come in and start off, kind of get those skills really early. So we try and give young people as many opportunities as possible. And then throughout their PhDs, if people come to Imperial to do a PhD, they often do internships in quantum companies. So they take 3 months out and go and work in a quantum company for 3 months. And it's great for the student because they learn a lot about doing work in the real world in these types of engineering places. But it's also great for the company because they really want to recruit. And so if they can get people enthusiastic early, it's brilliant. So we do that. And like I mentioned on the video, we're also really keen on training civil servants, so training people in politics, in government, about understanding the potential of these technologies, and actually also training end users. So how do you get people in banks or in car manufacture or in the health service to care about quantum? So there's lots of different ways in that. I think we're trying to think about how can we help everyone. Oh, and one more point that could be a collaboration with Ghana. We're very keen on helping investors, so that people who will invest in technologies, historically, it's been tricky to get them to invest in deep technologies, so technologies that are quite far away from delivering any kind of commercial benefit. So you know, quantum computers could be 10 years before they're making people lots of money. Quantum sensors will happen a lot quicker. But how do you get those venture capital or angel investors to invest their money? And that's something we're really focusing on this year, is helping them understand technologies better and what questions to ask so they can invest.
Well, thank you very much, Jess. This is really wonderful. I mean, it's really inspiring. I forgot how inspiring you are. But thanks for taking your time, and it's really been really helpful, I think. And there's a lot for people to start thinking about. So you've covered a lot of areas, including science communication and working with policy and bankers, et cetera. So thank you again. Let's thank Jess again for a wonderful talk.